What limits a population growth? What are the things that cause that curve to flatten out in a logistic curve? That is what we're going to discuss in this lecture. So I want you to be able to, at the end of this lecture, list and compare population-dependent and population-independent factors. Be able to relate predation and disease to population size, and be able to define the term stochastic. So first up, some density-independent factors. Density-dependent, dependent first. Let's say, for example, you have a herd of deer, and that herd of deer has a predator. Perhaps it is a cougar that lives in the area, and the cougar can prey on any one of the deer if it can sneak up on the deer and capture it. Well, it turns out that mortality may actually go down if there are more deer in the population, and that's what's called an inverse effect. It may go down because as a herd of deer has a higher chance of survival than a single deer. And this may decrease the mortality. So sometimes you have what's called an inverse density dependent factor where mortality decreases as population size increases. However, a lot of the examples we'll look at are going to be density dependent factors with increased mortality, such as predation. As the population of snowshoe hares, that's moose, as the population of snowshoe hares increases, the population of lynx will increase as well. Not only that, but as the population of snowshoe hares increases, the lynx are going to have an easier time finding any one given hare, given that they may be scattered relatively evenly across an area. The hunter's time to find something, their search time, is going to decrease as they are more likely to have a higher encounter rate as the population increases. If you're beginning to hear some reminiscences of the Lotka-Volterra equations, or if you're hearing some optimal foraging reminiscences, this is pretty much where it is. And Lotka-Volterra was showing that there is this bouncing back and forth between the populations of predators and prey, between snowshoe hare and lynx, for example, or between wolves and moose, where the number of wolves and the number of moose are going to be kind of inversely related to one another, because moose mortality is greater when there are more wolves. Now you'll notice as well that these are different scales, that there are a very much higher number of moose than of wolves, and we'll get to that whole rule of tens much later on. There can also be disease, of course. A disease can spread more easily through a dense population. Thus, it's a density-dependent factor. The higher the density of the population, the more chance that any infected individual will encounter an uninfected, susceptible individual. And when they encounter a susceptible individual, they're probably going to pass on the disease. If encounter rates are incredibly rare, that is probably because it's a very low density population, and therefore the disease will not spread. We could also mention the example of competition. This being specifically intra-specific competition, that if you were to put a certain number of cattle in a field, the amount of grass in the field is independent of the cattle at first, and then as the cattle begin to graze it, the amount that any cow can get in is 1 divided by the number of cows, a fraction of the field that is given to them. As that denominator increases, competition increases, and thus mortality increases as organisms cannot get enough food or sunlight to survive. Again, planting a whole bunch of seeds in a small area means most of them will die. I'm really hoping that's what's going to go on for my yard. Having rained recently, my yard is chock full of weeds. I mean, each one of them is like this big, but they're competing with each other. They're very dense right now. I really want to use herbicide, but I don't want to destroy all the good plants. You also have density independent factors. So these are going to be occurring regardless of what's really going on. So temperature changes, that's more of the air, the sunlight, the breezes. That's what's going to be influencing those temperature changes, not the number of deer in an animal area. Forest fires are generally density independent, unless you're talking, of course, about the trees. But if you're talking about the deer or the marmots or the squirrels, they're density independent. Rainfall and drought, come back to that in a minute. Or pollutants, these are density independent with regard to non-human animals. And we call these stochastic factors. It really means random. So stochastic really just means random, but you're thinking about the different changing factors. And this is a question I got asked once. How do you control for all the stochastic factors? Basically, that is to say, how are you sure your sample size isn't being influenced by randomness, just random rainfall? You have a thunderstorm in one area while you have no thunderstorm in another. The stochastic factors, the randomness of it all. And really, a large sample size takes care of stochastic factors because eventually you're going to include both the plant that got a ton of water and the plant that got very little water, but most plants got a medium amount of water. So you're going to get the average is going to be basically, well, the average of all the stochasticity that is out there in the world. So stochastic means random factors, and often these are density independent factors. So a common one to consider is drought or fire. And these two are very closely related, especially here in the Pacific Northwest, where a drier period can lead to fires. So here we have, however, the Galapagos, where, as you see, during 1 year, lush green area after a plentiful rain, and then the next year it was incredibly dry, almost desert-like, where you actually see the cacti surviving, but pretty much everything else has gone away. Now, if you were an animal living in that area that required some of this greenery to eat, then your population will suffer as you run out of resources. And that is exactly what Peter and Rosemary Grant saw in their book, The Beak of the Finch. So here we have some finches, and what you see is the number of seeds down in the way bottom there decreased between 1976 and 1977. And likewise, the number of finches decreased during this time. So it was the seeds that drove the finches down close to extinction, because it was a density independent factor, drought, decreasing the number of seeds, decreasing the number of finches. Cat. Fine, but you have to enjoy my lecture if you come in. The cat wants in. Of course you let the cat in. Well, fine. Yeah. This is Rosie, and she has been joining me on some of my lectures. Rosie, say hello to the students. Oh yeah, she doesn't speak English. And she's just getting in here because she wants a little bit of love, and she wants to get cat hair all over my vest, don't you? Anyway, there's your little cat break. Don't worry, we'll keep the lecture short. Cats are important. Ha! Now she's gone. That'll teach her. All right, this is close to the end. So, population growth and ranges. So I want you to think about cats. Now, no, that wasn't the planned example. We have two more examples, but... So, growth and ranges here. So, you've got a litter of kittens. And they're going to compete with each other for resources, so they're going to spread out as they grow up. Now, if they spread out too much, the chance of finding a mate goes down. So, to spread out too far from your home, your population center, reduces the chances of finding a mate and thus dying alone with no fitness. But staying close to your center where you were born is going to actually increase the chances of intra-specific competition and thus decrease your fitness. So there's a healthy balance here. And as a population grows, it can expand. What we have here is Africanized honeybees being introduced to Brazil in 1957. And as you see, they expanded their range continually. So they still have to be able to meet and mate and form hives. So they still have to stay within a certain population density. It's not very high for bees, but they continue to expand their range as their population increases. There's also the maple, which is increasing in population and growing as the ice age retreated. But also the collared dove was a good example. I don't remember which lecture I'm doing that one in, quite honestly. But the collared dove is an introduced species that essentially some of the organisms stay close to home, some of them fly far away. If they fly too far away, they don't mate. If they stay too close to home, they compete with one another. So the consequences of population growth there are that they have expanded their range, especially in the past couple of years. Anyway, short lecture, little kitten, enjoy.